So, hello, this is me, Aditya Tiwari, and I am starting physics daily problems from today. We'll be posting a physics problem daily, which is more related to conceptual understanding rather than mugging up the formula and solving a question. So, this is a very basic problem, testing your understanding on the concept of modern physics from Shashi Bhushan Tiwari, a famous book for JEE Advanced. This question is taken from the level 1 from that particular book. So you should first give it a try, then view the answer. So in the question, there is given as a light photon of wavelength lambda naught is observed by an atom of mass m at and rest in ground state. So let us assume that this atom is in the ground state and it has some wavelength coming as lambda naught. Now, if this particular atom is in ground state and it has received some wavelength of lambda naught, it will surely get excited because it has energy and it can freely move. At given in this question also, the atom is free to move, so it can freely move. But after absorbing the incident photon, it emits another photon in direction opposite to the incident photon. Means if the incident photon is coming from left to right, now uh, the re-emission of the photon or the photons will be in the opposite direction of the uh, coming photon like this. So we'll take it as lambda. So now it will have some kinetic energy. So you should think why it would have some kinetic energy. We'll discuss this particular thing why it will have a kinetic energy at last. So this is a basic concept of this question, like a lambda naught wavelength photon is coming and it is providing it some energy, so it is getting excited. Then again it is releasing the particular photon with same not same wavelength but wavelength opposite in the opposite to the that direction. So now it again comes to the ground state. Now we have to tell the lambda naught in terms of k and m. So first, basically, the basic thing we should know that in this particular case, the momentum is being conserved and energy is being conserved. So by applying these two, we'll get the answer very quickly. So first, we'll apply the momentum conservation. So while applying the momentum conservation, we know that the particular momentum of the initial would be h by lambda naught. So you may know that h by lambda naught is the de Broglie equation. If you are thinking that it is particularly long because the this particular equation was derived from Einstein's equation of momentum is equal to energy by speed of light, that is p is equal to e by c. So we write E as h nu by c. So by replacing it, we come across this equation. So now you'll wonder what de Broglie said. So de Broglie basically hypothesized this equation in respect to the waveform of the light, because waveform is surprising as it is traveling in a wave. Light can travel as a particle, we can understand that, but wave is a bit surprising. So to calculate the wavelength, it should be proportional to h by p. So this is particularly the de Broglie wavelength, de Broglie equation. So this is a basic concept. Now, if we see h by lambda naught would be equal to, we'll see that the kinetic energy is in the right side, so we'll take it as plus, so root of 2 mk plus, sorry, minus, because the new photons wavelength is traveling in the opposite direction, so it would be coming as h by lambda. So this is the first equation. Now we are applying the energy conservation. So while applying the energy conservation, we know that energy of an atom at its main state is hc by lambda naught is equal to, the energy is kinetic energy at right, so we'll take it as plus, then minus this particular kinetic energy would be hc by lambda. Now we'll be dividing it by C. You will know why we are dividing it by C. So it comes to be h by lambda naught K by C minus h by lambda naught. This is the second equation. Now we see that while adding 1 and 2, this thing get cancelled. So we get an equation in terms of h lambda naught 2h lambda naught is equal to K by C plus root of 2mk. So this is the final answer for this equation, as we have to find the relation of lambda naught in terms of K and M. So we have this is the final answer for this question. This question was pretty easy and basically testing your basic concepts on the particular question. Now the question arises why the particular system has gained the kinetic energy in the opposite direction of the photon that is emitted. So if you see a concept of rocket, you would know that. Let us assume this is a basic rocket. Now, if you see when a rocket emitted thrust, it goes in the direction opposite to the thrust. So, likewise, in this question, let us assume that this wavelength is the thrust for this atom. So, when you provide a thrust backward, according to the Newton's law, every action has an equal and opposite reaction. So, it must be gaining some kinetic energy in the opposite direction. So that's why it has some kinetic energy in this question. So yeah, this was a very basic question. You should give it a try, and we'll see you tomorrow. Bye bye.